We are discussing CPU scheduling algorithms. As we know, the task of the CPU scheduler is to select a process from the ready queue which will be dispatched to the processor next. Some algorithms we have already discussed. Let us see what are these algorithms. The first one we discussed is a first come, first served. Second is the shortest job first. Third we discussed is the priority scheduling. And the fourth we discussed the round robin. The assumption here is that we have a single processor. And mainly we have taken the waiting time to be a criterion, except round robin, where we took the response time to be a criterion. Now, today we shall be discussing two more scheduling algorithms. One is multi-level queue, and the second is multi-level feedback queue. These are the two algorithms that we'll discuss today. Before we start the discussion, let's revisit the process state diagram to have a very clear idea that when the CPU scheduling algorithm should be invoked. Okay, here the different transitions have been shown. The transition 1, 4 and 2. Okay, this 1, 2 and 4, this transition will invoke CPU scheduling, but in a non-preemptive way, because you know, if a process is in the running state, by transition 1, transition 2 and transition 4, it will leave the CPU. Therefore, the CPU is idle, and therefore a process which is waiting the ready queue will be dispatched. But CPU scheduling can be invoked under transition 3 and also under transition 4 if we are taking preemptive scheduling. Okay, which means that if the process that is coming over in the ready state is higher in priority than that one which is in running, and we are using preemptive scheduling, then this process will be stopped, taken out of the CPU, and this highest priority process which has just come into the ready queue will be dispatched to the processor. Okay, now let us see. Let us come to the next scheduling algorithm. We call it the multi-level queue scheduling. Here we have more than one ready queue with different priorities. Okay, we keep different priorities and more than one ready queue. An example can be that say foreground queue and the background queue. The foreground queue, there are interactive processes, and the background queue, the batch processes. Okay. Now each queue may have its own scheduling algorithm. For example, the foreground queue may run that round robin. The background queue, on the background queue, the algorithm may be first come, first served. Now, the scheduling must be done amongst the queues also. Now, there can be the fixed priority scheduling, which means that serve all the processes from the foreground and then from the background. Okay. Now, you see that may lead to starvation, because the background, if there are sufficient number of processes in the foreground queue, no process from the background queue can be taken at all, and in that case, no process from the background will be running at all, and they will be starved. Okay, they will never get the CPU, and that is why one solution can be that the time slice is allocated to the foreground and to the background, say 80% to the foreground and 20% to the background jobs. In that case, since the CPU time is shared between the foreground and the background, that 20% time at least the background jobs will be getting. Now here we have taken only two queues. One is the foreground queue and the background queue. In practice, of course, there may be many priority queues. Okay, as I have shown here. Here, say 1, 2, 3, 4, 5. The system gives 5 priority queues. Highest amongst them is that for the system processes, that means operating system processes naturally. The second highest is that interactive processes, to give the interactive processes a good response time. The third priority queue is editing processes. These are also interactive processes, and therefore they should have sufficiently higher priority. Next is the batch processes. Here's the response time problem, or the response time criterion is not there, and therefore they can have the lower priority. And in this particular system, the students' compilation processes have been given least priority. Now, this is a multi-level queues. One aspect of this multi-level queue is this: the processes cannot move between queues. That means once a process in one queue, it doesn't move to other queues. To circumvent this problem, what has been proposed is the multi-level feedback queue. Here, we have more than one queue, and the processes can move from one queue to the other queue, right? Now, naturally, for example, even say, for example, in these cases, possibly the processes can move between the different queues, okay? Now, the parameters under such circumstance is that number of queues, a scheduling algorithm for each queue. These two parameters are there also in the case of a multi-level queues. But what more parameters come is a method used for promoting a process. That means if a process is one queue and some criteria, depending upon certain criterion, the process can be promoted to a higher priority queue. Okay, that criterion has to be defined, and the algorithm should work on that criterion. Similarly, that method used for demoting a process, say some processes is there in one queue, and due to certain reason, it is decided that this process should now get a lower priority than the process than it is occupying now, and therefore we'll have to have a method for demoting a process also. And naturally, method used for entering a process into a queue. If a process comes to join a queue, which of these queues it joins? Now, as an example, we have taken one case, which three queues, say Q0, Q1, and Q2. The time slices given to Q0, Q1, and Q2 is 10 millisecond, 20 millisecond, and 60 milliseconds. Priority is 0, 1, 2, respectively. This is the highest priority, and the scheduling policy for Q0 is first come, first served. For Q1 is first come, first served, and for Q2 is a round robin. Now, the different methods are there. For example, for the demotion, that on completion of time slice, that means, for example, if a process is there in Q0 and it has been dispatched, and on the processor it has consumed the entire quantum of 10 millisecond, right? In that case, the process can be declared at that instant of time to be CPU bound, and that can be demoted, because the policy may be that give IO bound job higher priority so that all the IOs remains occupied. Okay, in that case, temporarily the process which has consumed that entire time slice can be demoted from say Q0 to Q1. Similarly, if Q1 a process consumes the entire time quantum of 20 milliseconds, it may be demoted to the Q2, which is for the hard CPU bound jobs. That means it is consuming much more CPU, and very seldom it is requesting IO. Okay, and similarly, the the promotion may be on aging, because you know that the priority, as I said, the priority of Q0 definitely is highest, and therefore all the time if there are jobs in Q0, then processes in Q1 and Q2 will never be served, and therefore they will starve. One promotion policy that we can take is that on aging, okay, by aging I mean the time that it's spent in a particular queue. On aging, it can be promoted to a higher queue. And entry, as we have said, is for the demotions or the promotions is decided by the policies, and initially the entry would be to the queue to which priority the process belongs. Okay, therefore these are in fact all the scheduling algorithms we wanted to discuss. Now let us make a summary of all the scheduling algorithms and see the criterion. The first one is the first come first served. Here the waiting time depends heavily on the arrival order, as we have seen, and there can be a convoy effect. By convoy effect we mean that the short processes will queue up behind long process, which may lead to either CPU being idle or the IO being idle. Okay, that's the convoy effect. Second that we discussed is the shortest job first. Now the shortest job first works on the predicted next CPU burst, and we computed the next, we predicted the next CPU burst by following what we call that exponential averaging. Here two schemes we discussed. One is a non-preemptive one, another is a preemptive one. It has been seen that SGF is optimal, which means gives minimum average waiting time. Third algorithm that we discussed is a priority scheduling. Here also the two schemes may be there. One is a non-preemptive and the other is a preemptive. The problem is once more starvation. Low priority processes may not get the processor, and the solution, as we saw, is aging. Okay, that means increase the priority on aging. The fourth that we discussed is that round robin is based on time sharing on time quantum, and the performance depends upon the time quantum that is allocated. Now, if the queue is too large, then the behavior will more or less will lead to, will be like FIFO, that is fast in, fast out. That means the large time quantum is allocated, the behavior of a round robin scheduling procedure will be similar to the FIFO scheduling procedure. And if Q is small, if we make Q too small with respect to the overhead, naturally that will increase the overhead because too much of switching from one process to the other will take place, and in that case too much of overhead will be involved, and naturally the system efficiency will go down. Therefore, we will have to choose a proper Q value so that the round robin performance turns out to be optimum. And the fifth and sixth one that we have discussed right now, the multi-level queue. Here we have more than one queue, and it's a fixed priority to queues may lead to starvation, which led to that multi-level feedback queue where processes can move between various queues. The process can be either upgraded or downgraded in terms of the priority, therefore in terms of the queue. Now this is so far as single processor scheduling algorithms are concerned. Now let us see the situation where we have more than one processor. We call it a multiprocessor system. But before that, let us see that what is our computation model. The computation model that we have till now is this, that we have a single CPU, a memory unit, that instruction stream coming from the memory, and the data stream that can come and go into the memory. Such a situation we call single instruction stream, single data stream situation. Naturally, there are variations of it in the case of a multiprocessor. The different variations have been tabulated here. This classification is by Mr. A.M.J. Flynn, done in 1966, and still is in vogue. That SISD, that means single instruction stream, single data stream, as I have told. There can be SIMD, that means single instruction stream and a multiple data stream, which is the situation in the case of an array processor, that one instruction that executes on multiple data, the portions of that array. Okay. Therefore, one control unit, many processing unit. Then there can be multiple instruction, single data stream, okay, MISD. This can be the situation in the case of a fault-tolerant machine, where the same process is executed on different data, and in the case of a failure, the majority voting is taken to accept which is a correct result. There can be MIMD, that means multiple instruction stream, multiple data stream. Okay, here each process independently run its each processor runs its own process with its own data and communicate between the amongst other processors. That's called that multiple instructions, multiple data streams. Let me repeat that here each processor has its own process and its own data and communicate with the other process running in the other data. Okay. Now let's try to give a overview of this MIMD architecture. This is an overview that have been shown. There are more than one central processing units, CPU 1 to CPU K, which is hanging on the global bus. There is a global memory. Processes are executed in the global memory by each CPU. The shared data is also in the global memory. Naturally, the global bus has to be very fast because bus contention are there, which has to be resolved. And since they are sharing same data, also the coordination amongst the different processes running in different processors have to be ensured and enforced. Such a situation we call a tightly coupled system. Here we have kept an global I/O processor also, to which the peripheral buses, that means SCSI or PCI bus, has been attached. As an example I have shown here, that similarly the LAN connections is also to that I/O processor. Now these CPUs which are hanging on this global bus can be of same type, can be of different types. If they are of the same type, we call it homogeneous multiprocessor system. Now the advantages are many naturally. It speeds off the entire computation. The system, total systems is now very fast and the throughput increases. One of the CPU fails, then it can be plugged off and the computing systems gracefully degrade. If you want to enhance the performance, put in another processor here. Okay, it will increase the performance till bus congestion does not come into the picture. Bus congestion doesn't come into the picture. Bus contention is always there. Okay, such a situation that when you can go on adding processor to speed up the computing throughput is called a scalable architecture, and this is very amenable to scalability. Right. Now, in the case of a multiprocessing system, the scheduling algorithm naturally will be different. One can have what we call the symmetric multiprocessing. In the case of a symmetric multiprocessing, each CPU executes the CPU scheduling algorithm, takes a process from the ready queue and executes it. Okay. In the case of an asymmetric multiprocessing, one of the CPU, say either CPU 1 or CPU 2 or CPU K, is designated as master. That takes a job from the ready queue and assigns it to different processors as a processors or fee. Now that is such a situation where the different CPUs are sharing a global memory is called a tightly coupled system, as against a loosely coupled system where the CPUs have their there's no global memory as such. The global memory is absent. There is global I/O is also absent. The situation is this, that CPUs are all independent naturally they'll have to have their own local memory and the local I/O. That means they have the CPU1 has its own memory and I/O. CPU2 has own memory and I/O. Okay. In that case, they simply are independent of each other, except that if one process running in CPU1, say, wants to communicate with another process running in CPU-K, message passing is involved. Now, this is what we call a loosely coupled system where the global memory is absent. Of course, in the tightly coupled system also, the CPUs can have their own local memory and the local I/O. In that case, a process is downloaded into a local memory and that CPU executes that process. Now, that's more or less what's the overview of the multiprocessing that we wanted to discuss here is that. Now, only one point I would like to mention here, that since this bus can be the bottleneck of computation speed up, because all the CPUs are utilizing this common bus in the case of a loosely coupled system. In place of a bus, there is sometimes what we call an interconnection network between the CPU. Okay, say this is the interconnection network that connects the different CPUs. There are various interconnection networks, which naturally is beyond the scope of this lecture, but this interconnection network speeds up communication between the different CPUs. That's all so far as our multiprocessor architecture is concerned. Let me summarize that what I have said in the case of a multiprocessor scheduling, that we assume homogeneous processors. Naturally, MIMD architecture is assumed here, and a tightly coupled system is assumed. Load sharing is done by keeping only one ready queue, and it can be symmetric multiprocessing or it can be asymmetric multiprocessing. In the case of a symmetric multiprocessing, each processor is self-scheduling. That means it goes to the ready queue, takes a job, and executes executes it. Okay. Now, naturally, the complexity arises due to sharing of system data structure. Would have to enforce coordination and communication, okay, and synchronization. That will be the point of discussions of our next course of lectures. Another is that asymmetric multiprocessing, as I was talking of, is the master slave structure is there. Master taking all scheduling decision, and also it is doing all the I/O processing. Now, that's all so far as multiple processor scheduling is concerned. Now, let's go to that another scheduling scenario, which we call that real-time scheduling. In the case of a real-time scheduling, we can have either hard real-time systems or we can have soft real-time computing. Okay, in the case of hard real-time systems, that a critical task has to be completed within a guaranteed amount of time. That means if a task is there and it requests processing, then that task has to be completed within the guaranteed time. That's called a hard real-time system. And in comparison to that, we can have that soft real-time computing. In this case, that requires that the critical processes have higher priority. Okay, it's not as demanding as a hard real-time system, where that guaranteed response time has to be honored. Okay. Now let us see, in the case of a soft real-time computing, what should be the criterion? The criterion is that the system should have the priority scheduling. Naturally, that real-time system should have higher priority. The priority must not degrade to aging. Since it's a real-time system, you cannot allow the degradation of the priority of a process, and the scheduling policy must be preemptive to provide a low dispatch latency, in the sense that if a real-time system comes from the ready queue, in that case, if there is a process that is executing the processor which has a lower priority, then that process has to be detached from the processor, and this process having that higher priority, the real-time process, has to be dispatched immediately. Now, in the case of a hard real-time system, of course, no compromise is allowed, and therefore, generally it is composed of special purpose software running on hardware dedicated to their critical process. Now, situation may be such even that the demand for meeting the response time is such that you cannot have any data in the secondary storage even. All such data that may be needed for processing is kept in the ROM. Okay, and similarly, any working place where the computations will be done has to be a very fast memory. That is why in the case of a hard real-time system, that the software runs on a hardware dedicated to their critical process. Okay, situations may be that, say for example, machine control, so oven control, chemical plant control, even say nuclear plant control. Okay, in such a situation, for example, in the chemical plant process or a nuclear plant process, so there cannot be any degradation in any way of the response time, meeting of the response time. You will have to meet the response time, and therefore the system has to respond to it. And such cases only can be made sometimes with dedicated hardware. But just to give you a glimpse of that of a hard real-time system, how a computer is interfaced, let me come to that interfacing external devices, this plate once more. Here we have said that, say, this is that I/O module interface port through which the I/O module communicates to the CPU. Here is that interrupt request line, here is the interrupt acknowledge line. This is, we said, is a device controller, and this is the input coming from that environment. Okay. Now, in the case of a keyboard, it is simple that you press a key and the data comes over to here. But if this CPU or if this system has to act as a controller of, say, either a machine or say an oven or say a chemical plant or say for example a vehicle or say from a nuclear plant, in that case the responses comes from this environment through the sensors into the controller over here, which is transmitted to the I/O port buffer. Okay, this whatever signal comes through, which is collected to the sensor, is converted from analog to digital form and then is passed on to the buffer, right? And as the input comes, the interrupt request is done to the CPU, and this interrupt request that is here, that interrupt request immediately invokes that scheduler, that job corresponding to this response, okay, corresponding to this excitement that is coming from that input, okay, that coming from the environment, will immediately invoke the scheduler that is there in the memory, and it will execute on this data that has been placed on the buffer. The controlled information should come possibly to another buffer, okay, in another I/O port, and from there the output should be given to the environment to control the cause of this excitement. Okay, for example, it can be a motor control, it can be opening of valve in a chemical plant, or it can be shutting down of a process in the case of a chemical plant. Therefore, the situation that I wanted to just show here is that interfacing remains the same, that environment, from that environment, signals is coming from, say, a hard real-time system. The moment that interrupt request comes, the CPU scheduler has to be invoked immediately. The computation is done in that interrupt processing, interrupt handler, okay, and the output is generated, which is sent to the environment to control the cause of excitement. Okay, and that is the real-time systems, hard real-time system, where you have to use very dedicated hardware if need arises. That's all so far our scheduling algorithms are concerned, and the scheduling environment, the environment under which scheduling are performed. Now, there are various scheduling algorithms that we have discussed. There should be some algorithmic evaluation of them. That algorithmic evaluation can be done in two ways in general. Okay, one is called that queuing model. In that queuing model, we assume a probability distributions of arrival rates and the service rates, and then you compute the CPU utilization, average queue length, and average wait time, etc., by queuing network analysis. And another is by simulation. In the case of a simulation, there are special simulation software, simulation packages that are available, and where you can model your queues, model your servers. Okay, you can define your arrival rate, service rate, etc., as parameters, and then you run the system, okay, to implement various algorithms and see what's the response time, what's the wait time, what's the throughput, etc., and then decide upon a best algorithm on a particular kind of processes that are there. Okay, in both this queuing model as well as that simulation procedure, both are very common, but naturally is outside the scope of our lecture. And with this, I would like to stop our scheduling algorithm discussion. Thank you.